Hi, guys. As our AP class starts, one of the things that we really focus on a lot throughout the course of the year is explaining and describing and coming up with explanations of stuff. And one of the areas that we really work through is um, motion and mechanics. Mechanics is a study of motion and its causes. But the first part of what we do is not look at the causes of motion or changes in motion. We just look at the motion itself and describe it. And that's what we call kinematics. So we live in a three-dimensional world, but we're going to talk about one-dimensional kinematics and simplify it down to make sure that we have one dimension down, and then we're going to add dimensions of study. So this is chapter 2 in the textbook. The questions of chapter 2 are what we're going to be working on in this next week here. But wanted to start about that. And today I want to talk about how we represent motion visually and some of the terminology. So one of the things when we talk about motion, if I were to see you in class right now, I would ask, are we moving? And can you make an argument that we are moving? Or can you make an argument that we are stationary? And you should be able to make that argument either way. We are moving compared to the sun, compared to the center of the earth, compared to other planets or other celestial bodies. And we're moving compared to somebody else that is moving. But we are stationary when we're sitting still compared to the classroom that we're in, or compared to the desk that we're sitting in, or our room that we're watching this video in. So motion is relative. So when we talk about motion, we have to have a good way of communicating what we're talking about motion compared to. So it's up to us to communicate what we consider to be stationary. All right? There's nothing in the universe that is stationary. We don't know of anything that is the point of the universe that can be measured stationary. But we can say, okay, I'm going to treat this room or the ground as stationary for my purposes. So we want to break down motion into looking at that. So you can see here, this person walking, we set an origin of x equals 0. So we use x to mark a position. And from left to right, we have a positive direction. So direction is an important aspect about it. So xi is initial position, xf is final position. So this person has moved in a positive direction. So they have a different position from initial to final. But we have to talk through that and make sure that when we're describing that the people who we're describing it to understand what we mean by that as well. All right. Some of the terms that we use in here will be a little bit different than what we use them in normal conversation. Some are the same. Some are a broader definition. Some are a narrower definition. Distance, same as what we're used to. Distance is how far, the total length of motion. All right. We like thinking in miles when we talk about it in the United States. Our base unit for distance in physics is going to be meters, but let's look at this example for miles. If you start at your house and go to the grocery store and back, you've got 8.6 miles. That's what's going to read on your odometer. Okay. If you were to go to your friend's house and back, your odometer is going to read 4.2 miles. But if you talk about displacement is different than distance. Distance is just a raw value number. It's always a positive value that tells you how far you have gone overall. Displacement is how far away you are from where you started and in what direction. So displacement includes direction, and it doesn't care about the route that you took. So driving from your house to the grocery store, you've gone 4.3 miles, but then if you drive to your friend's house, you go 6.4 miles in the opposite direction. So you are actually 2.1 miles from where you started. So that's your displacement. And since we're treating the grocery store's direction as positive, we would say your displacement is negative 2.1 miles. because you're ending up 2.1 miles in the opposite direction of the positive. Now, your car odometer is going to read 10.7 miles. So displacement and distance are different. Displacement includes direction. It can be positive or negative when we're talking about one-dimensional motion. One-dimensional motion is forward and backward, up and down, left and right. So it just is one direction or its opposite direction. So it's the simplest type of motion to analyze. We're going to start simple and go from there. All right. Average speed is exactly what we think of, and that's what we tend to look at when we are trying to figure out how long it's going to take to get someplace. We're generally, instead of doing an average speed calculation, which would be simply, we use V, but and I'll talk about that in a second. Distance divided by time. Usually we're more concerned about the time. 90% of the time when I ask someone how far is it to the Mall of America, they're not going to tell me the distance in miles or kilometers. They're going to tell me it's about 15 minutes. Because they've already, they decide that I must care about how long it's going to take me instead of how far it actually is. Well, if I have a car that has 10 miles worth of gas in it and it's 12 miles to the Mall of America, I might be more concerned about how far is it rather than how long it's going to take me. But generally speaking, we're usually concerned about how long it's going to take us to get somewhere. I ask someone how far is it to Chicago, they're not going to say 395 miles, they're going to say it's about 6.5 hours. And because the normal conversation, we're looking at time more emphasized than speed. But average speed is distance divided by time. All right. So here's a situation. I'm going to leave this on the quiz at the end of the video lesson. Average speed of the red car. It goes 4 miles at 30 miles an hour, 4 miles at 50 miles an hour. Does it average 40 miles an hour? All right. So I want you guys to think about that and end up, we're going to figure that out in the quiz. Okay. Now, average speed is, remember, speed is distance. Distance is a positive value. It just measures how far you've traveled and how long it took. So that's what your odometer divided by time is. My wife and I, many of you guys have had my wife or have my wife in math right now. We're kind of nerdy. One year we went on a road trip and we had a car that did not have a working speedometer. So interestingly enough, I had a stopwatch and a calculator in the glove compartment. So we're in the middle of Montana when there's no other cars around us and we're trying to figure out how fast we're going. So we would time the time between mile markers on the interstate, and she would calculate out how long or how fast we were going by taking the time and the distance. 1 mile divided by 54 seconds, for example, is 65 miles an hour. I still remember having done that road trip. So then we would make it a challenge, and I would try to go 5 miles at the same speed. So we would time at 5 miles and see, did it work out that I was going the same speed or did it not? Middle of Montana, back in the 90s, all you had was country music radio stations or no radio stations at all. And we got bored, so we're driving along with a car with no odometer or speedometer, so we figured out our own entertainment. Believe it or not, true story. Okay, so that's average speed. Average velocity, the slight difference here, is displacement divided by time. So displacement, remember, has a direction. So it can be positive or negative. So if we look at this example of this person going from 0 to 50 on the top, they're sprinting from 0 to 50, they're going to have a positive average velocity. I don't know how long it took them, but they're going to have a positive average velocity. But as they walk back from 50 to 0, they're going to have a negative average velocity, and it's going to be a lower value because it's going to take them longer. all right? We tend to use velocity more than we do speed in here because direction is important, especially in one-dimensional motion. So when direction is important, we look at velocity instead of speed. All right, so when you return your starting point, your average velocity is 0. Indianapolis 500 is a 500-mile car race that goes around an oval, starts at the same spot that it ends at. The finish line is the same as the starting line. So the average speed of the winning car of the Indianapolis 500 maybe is 200 miles an hour because they went 500 miles in 2.5 hours. That's 200. But the average velocity of the car is 0 because its displacement, which is the comparison of where it starts to where it ends, is 0. So if you end up in the same spot that you started, your displacement is 0, so your average velocity is 0. So if you start the day in your bed and travel all over, running errands or doing whatever, and end up in the same spot, your average velocity over the course of the day would be 0, even though you were going all over the distance traveled, and your average speed would not be. All right. We use graphs oftentimes to give us a quick way to interpret and visualize motion. This is the same sequence of motion on a number line type of graph and on a position versus time graph. The position versus time graph gives us a little bit more information and is more commonly used. So we're going to talk about how we use those and what we interpret on those. These are showing the same sequence of motions of an object, one object, for 4 seconds worth of motion, a little bit beyond 4 seconds worth of time. And we see that it starts at a position we designate as 1 meter, positive 1 meter from the origin, and it ends at a position negative 1 meter from the origin. We can actually figure out what the average velocity is, because the average velocity would be negative 1 meter divided by 4, so it's got a average velocity of negative 0.25 meters per second. But that's obviously not how fast it was going at any point in time. So when we talk about that, we see a lot of different information on there. So here's an example of a position versus time graph. We use these a lot, and you need to be able to interpret what's going on. So this is a sequence of motions of this car. It starts at the origin. It's 10 seconds worth of time, and we see how it moves. Okay, speeds up a little bit, stops for a while, and then goes back and forth, reversing direction. So think about what's going on at different points in this graph. This is telling us where the car is at any point in time because it's a position versus time graph. Okay, but it's got a lot more information than just that. So when we look at position versus time graphs, they really contain a lot of information. We always arrange them so time is the independent variable because time is going to go no matter what if an object is moving. So time is always the x-axis, horizontal axis, and position is always the vertical axis. All right. We're going to talk about instantaneous velocity. That is a velocity at any instant in time. We've talked about average velocity and average speed. Those are over the course of a time period. But instantaneous is what is the velocity at that instant. Is it positive? Is it negative? Speed is simply the numerical value of velocity. So how fast is it going? So your speedometer of your car measures instantaneous speed. It tells you how fast the car is going. It does not tell you what direction it's going. All right? I believe, and I haven't tested it out, but I believe if you put your car in reverse and speed it up, the speedometer should oftentimes move, but it won't tell you it's going in reverse at that speed. It'll just tell you it's going at that speed. I should test that out at some point in time, but I also want to be safe. All right? You don't need to know its formula, but this is just telling us what the definition of instantaneous velocity is, and that's when we're looking at the change in position over a smaller and smaller increment of time. As the limit as time approaches 0 of the change in position. So when you see delta, delta x is change in position. That's what we call displacement. Delta t is change in time. So the smaller the increment of time, the larger the increment of displacement, the larger the value, the numerical value or magnitude of velocity. Okay, so your speedometer on your car tells you what your instantaneous velocity is. It doesn't tell you your average, but it tells you how fast you're going at that instant in time. If you drive to school, at some points in time, you might be going 30 miles an hour. At some points in time, you might be going 0 miles an hour. But if you're going 0 miles an hour, that's your instantaneous velocity. And if it stays at that, you're never going to get to school. But you average maybe 10 miles an hour because of the traffic and those annoying freshman parents that are dropping off their kids in front of the school. So if we graph out a position versus time graph, the average velocity takes place over a course of time. So this lowest green bar is the average velocity for 2 seconds worth of motion. So it's gone 26 point, or 20, well, it looks like 27.4 is what they think, 27.4 meters in 2 seconds. So it's gone 13.7 meters per second as an average. But at any point, the instantaneous velocity is the slope of the line. So at 1 second, the slope of the line is that upper green line, which is 10 meters per second. Okay, so it's tangent to the curve. Same thing here. The slope is the average velocity. If we look at the slope between T1 and T2, it's the average of the slopes between that time. Slope between T2 and T3 is average velocity. The slope at T3 is instantaneous velocity. All right. So looking at that motion of the car once more, these are questions I'm going to ask you on the quiz at the end of this, or the questions for the video lesson. What does the slope of the graph tell us? What's happening when the graph crosses 0, and what time periods have the same velocity? And how do we tell that? Notice this is not a velocity versus time graph. This is a position versus time graph. How do we know what the velocity is? What's going on with that? So those are some questions you need to be able to answer when you look at a position versus time graph. Now, position versus time graph has the most information of any type of motion graph. We call it D versus T or X versus T, displacement versus time graph, or position versus time graph. It tells you where an object is. It tells you its displacement. So if we compare where it is compared to where it was, and it tells you its velocity, which is actually the slope of the graph at any point in time. It also tells us acceleration. So think about what it would look like if it was accelerated. All right, we'll stop there. Next lesson, we'll talk about velocity versus time graphs and acceleration. All right, thanks a lot.